keep going. Let us continue the fourth part of colligative property, that experimental determination of elevation in boiling point by Landberg's method. Let us try to understand the figure first. It consists of an outer jacket B and it has an inner tube A. That inner tube consists of a thermometer and connected with a steam glass tube. Now let us come back. Elevation in boiling point delta Tb is given as delta Tb is equals to T1 minus Tb, where T1 and Tb are boiling points of solution and solvent respectively. By determining T1 and Tb experimentally, delta Tb can be calculated. The boiling point of solvent and solution can be determined by passing steam, as shown in the figure. The apparatus consists of a inner tube or boiling tube A carrying a bent tube and 1/10 degree thermometer. This tube is provided with a bulb containing a hole at the center. This inner tube is surrounded by an outer jacket B. The tube A is washed well and solvent is taken into it. Steam is passed into inner tube by means of bent tube. Steam bubbled out and condensed in solvent. Because of this, the temperature of vapor pressure of solvent increases. When vapor pressure of solvent becomes equals to atmospheric vapor pressure, the solvent begins to boil and temperature remains constant. This temperature is noted on thermometer and this is the boiling point of solvent T. Less volume of solution is prepared by dissolving W grams of solute in a solvent. This solution is transferred to clean inner tube and boiling point of this solution is determined. Let it be T1. After the experiment completes, the volume of solution is measured. From this, weight of solution can be calculated. Therefore, delta Tb is equals to T1 minus Tb. Substituting the value of delta Tb, W and X, the molecular weight M can be calculated. M is equals to 1000 kb W by delta Tb into X. Now let us discuss the next topic, that is depression in freezing point or cryoscopic constant. Freezing point is a temperature at which solid and liquid state of a substance have same vapor pressure. The vapor pressure of solvent is higher than that of solution. As a result of that, solvent freezes at higher temperature than solution. This means that the freezing point of solvent is always higher than freezing point of solution. Like Tf and Tn are freezing points of solvent and solution. Therefore, delta Tf is equals to Tf minus T1, where Tf is called as depression in freezing point. After understanding the freezing point, now let us come to the next topic, that is relationship between delta Tf and lowering of vapor pressure. Here we have plot a graph of vapor pressure versus temperature. It also consists of three curves: solvent, solution 1, solution 2, where to a solvent you can see vapor pressure of P0 and temperature Tf. Solution 1 P1, temperature T1. Solution 2 vapor pressure P2 and temperature T2. Let us consider the variation of vapor pressure of solvent solution 1 and solution 2 with temperature at A and a pressure P0. Temperature is Tf. This is called as freezing point of solvent. Similarly, at B, vapor pressure is P1 and temperature is T1. At C, vapor pressure is P2 and temperature is T2. Therefore, T1 and T2 are the freezing points of solution 1 and solution 2. These curves represents variation of vapor pressure of solvent and solution in liquid state and in solid state up to freezing point. The equilibrium present in between liquid and vapor. After that, the equilibrium is between solid and vapor, that is called as sublimation. Since solutions are dilute, the curves are assumed that they are parallel to one another. Let us consider similar triangles ABE and ACD from the previous graph. Therefore, AD A by AE is equals to CD by BE, where P0 minus P2 by P0 minus P1 is equals to Tf minus T2 by Tf minus T1. Therefore, delta P2 by delta P1 is equals to delta Tf2 by delta Tf1. Generally, delta P is directly proportional to delta Tf, call it some equation 1. Therefore, depression in freezing point is directly proportional to lowering of vapor pressure. According to Raoult's law, P0 minus P1 by P0 is equals to x2, where x2 is the mole fraction of solute and is given as x2 is equals to small n by capital N plus n, where small n is very small, it can be reduced. In the denominator, we get x2 is equals to capital small n by capital N. Therefore, P0 minus P1 by P0 is equals to small n by capital N. Delta P by P0 is equals to n by n. Therefore, delta P is directly proportional to small n by capital N. Call it some equation 2. From equation 1 and 2, delta Tf is directly proportional to n by capital N. Here it is a colligative property. Let W grams of solute of molecular weight capital M is dissolved in X grams of solvent of molecular weight small m. Small n is equals to W by M and capital N is equals to X by small m. Therefore, delta Tf is directly proportional to Wm by M into X. Therefore, delta Tf is directly proportional to M into W by M into 1 into X. Let us consider that 1 mole of solute is present in 1 kg of solvent. Therefore, W by M is equals to 1 and X is equals to 1 kg. The above equation becomes delta Tf is equals to constant into M into W by M into 1 into X. Delta Tf is equals to Kf W by M 1 by X, call it some equation 3. After reducing to W by M as 1 by X 1, the equation reduces to delta Tf is equals to Kf, where Kf is the molar depression constant or cryoscopic constant. Kf is defined as the depression in freezing point produced theoretically when 1 mole of solute is dissolved in 1 kg of solvent. Let us consider the equation 3. Delta Tf is equals to Kf W by M into 1 by X. Mass of solvent X is M expressed in kg. Delta Tf is equals to Kf W by M into 1 by X by 1000. Delta Tf is equals to 1000 Kf W by M into X. Therefore, M is equals to 1000 Kf W by delta Tf into X. Now let us come to the next topic, that is relationship between Kf and latent heat of fusion. Here also we need to plot a graph of vapor pressure versus temperature. It consists of two curves, solvent and solution at P0 Tf and solution at P1 T1. Let us consider vapor pressure temperature curves for a solvent and a solution. On cooling, the vapor pressure of solvent goes on decreases at a point A as shown in the figure. The vapor pressure of solvent in liquid state becomes equals to the vapor of the solvent in solid state. The temperature at that point is called as freezing point of solvent Tf and vapor pressure is P0. Similarly, T1 is the freezing point of solution. At that point, P1 is the vapor pressure. These curves consist of two equilibrium as liquid vapor and solid vapor. Let us consider the solid vapor equilibrium along the line AB. By applying Kayser-Clapeyron equation between points A and B for equilibrium of solid and vapor, we get ln P0 by P1 is equals to delta Hs by R into Tf minus T1 by Tf into T1, where delta Hs is molar heat of sublimation. Since solutions are very dilute, Tf T1 is similarly to Tf square. Tf minus T1 is equals to delta Tf. The above equation becomes ln P0 by P1 is equals to delta Hs by R into delta Tf by Tf square. Call it some equation 1. Let us consider an equilibrium of liquid and vapor at point B and C. By applying Clapeyron equilibrium, ln P by P1 is equals to delta Hv by R, Tf minus T1 by Tf into T1. Ln P by P1 is equals to delta Hv by R into delta Tf by Tf square, where delta Hv is the molar heat of vaporization. It can be written as minus ln P1 by P is equals to delta Hv by R delta Tf by Tf square. Ln P1 by P is equals to minus delta Hv by R into delta T by Tf square. Call it some equation 2. By adding 1 and 2, we get ln P0 by P1 plus ln P1 by P is equals to delta Hs by R into delta Tf by Tf square plus minus delta Hv by R into delta Tf by Tf square. That is equals to delta Hs by R delta Tf by Tf square minus delta Hp by R into delta Tf by Tf square. Ln P0 minus ln P1 plus ln P1 minus ln P is equals to delta Tf by R Tf square considered as a common. The remaining term is delta Hs minus delta Hp. The next equation becomes ln P0 by P is equals to delta Hf into delta Tf by R Tf square. Call it some equation 3, where delta Hf is called as molar heat of fusion. Let us consider ln P0 by P. The next equation becomes ln P0 by P is equals to minus ln P by P0, that is equals to minus ln into 1 minus P0 minus P1 by P0. We know that 1 minus ln 1 minus x is equals to minus x, where x is very small. Therefore ln P0 by P is equals to minus of minus P0 minus P by P0 is equals to P0 minus P by P0. Call it some equation 4. Therefore P0 minus P by P0 is equals to delta Hf into delta Tf by R Tf square. Call it some equation 5. By Raoult's law of relative lowering of vapor pressure, P0 minus P by P0 is equals to x2, where x2 is a mole fraction of solute. x2 is equals to n by capital N plus small n. Since solutions is dilute, small n can be neglected. x2 is equals to n by capital N. Let us consider a dilute solution containing W grams of molecular weight capital M in X grams of solvent of molecular weight small m. P0 minus P by P0 is equals to n by n. That becomes W by m whole divided by x by m, that is equals to Wm by x into m. Call it some equation 6. The above equation becomes delta Hf into delta Tf by R Tf square is equals to Wm by x into m. Therefore delta Tf is equals to R Tf square Wm by h delta Hf x into m, because delta Hf is equals to LFm, where LF is the latent heat of fusion. The above equation becomes delta Tf is equals to R Tf square Wm by LF x capital M small m. Small m on either side get cancels. The equation becomes delta Tf is equals to R Tf square W by LF x into m. Call it some equation 7. Let us consider 1 mole of solute in 1000 grams of solvent. W by m is equals to 1, x is equals to 1000. The above equation becomes delta Tf is equals to RTF square by LF 1000, that is equals to Kf, where Kf is a cryoscopic constant. Kf is defined as the depression in freezing point theoretically produced when 1 mole of solute is dissolved in 1000 grams of solvent. Kf is equals to RTF square 1000 LF. Therefore 1000 Kf is equals to RTF square by LF. Call it some equation 8. Adding by equation 7 and 8, we get delta Tf is equals to 1000 kfw by m into x. Therefore m is equals to 1000 kfw by delta Tf into x.